On the third planet, orbiting an average yellow dwarf star, a curious creature evolved. Humans. So curious, in fact, they couldn't stop themselves from trying to figure out how everything worked. Although their simple brains were evolved for a hunter-gathering life, somehow they were not content with what they could see with their eyes and feel with their hands. So they invented telescopes to peer into the depths of space and particle colliders to smash matter into its constituent parts. And eventually they discovered how everything in the universe actually works. Although they didn't actually manage, did they? Not yet, anyway. Excuse me. So here's the problem. We've got two fundamental theories that describe the universe, but we don't know how to join them together. On one end, we describe how the fundamental particles work and interact with each other with quantum field theory, which explains electromagnetism, the nuclear strong and the nuclear weak forces. And at the large scale, the theory of general relativity explains how objects influence each other due to the curvature they make in space-time, otherwise known as gravity. These two theories are the most complete description we have of how the universe works, and both have been tested and verified to incredible precision. But they don't go together. Gravity isn't described in quantum field theory, and general relativity says nothing about the quantum world. Big deal, you might say. If they're each doing their own bits okay, then there's no problem. But there is a problem. In between these two theories live two of the biggest mysteries in physics, black holes and the Big Bang. In these extreme events, quantum mechanics and general relativity meet. We won't ever be able to understand them until we develop a theory of quantum gravity, the fundamental theory of everything. We've made some attempts, the most promising are string theory, or M theory, and loop quantum gravity, but neither of these have got experimental evidence to back them up. For example, string theory predicts new fundamental particles called supersymmetric particles, which we haven't observed. So for now, these theories remain hypothetical. I should mention that in practice, we don't only use quantum field theory and general relativity to model everything in physics. Often they would be far too cumbersome, so we actually use a whole suite of other theories that are perfectly good approximations for those specific situations. But quantum field theory and general relativity are special because they're the most fundamental theories. So why has it been so long since we had any progress on quantum gravity? General relativity was published in 1915 and quantum field theory was completed in the late 1970s. Why has there been very little progress since then? Well, there's one simple reason. The force of gravity is so much weaker than the other forces, and so making an experiment where something significantly feels all of the forces at the same time is very, very difficult, perhaps impossible. Gravity only becomes strong when you're dealing with very large amounts of matter. For example, it takes the whole Earth to keep you on the ground. And for stuff this big, like humans or planets or stars, quantum effects just aren't noticeable. The place where quantum physics is important is down at the scale of atoms and subatomic particles. And these things are so small and light that the force they feel due to gravity is negligible compared to the other forces. For example, two electrons, a centimetre apart, would feel a repulsion from their electric charges, but attract each other due to their mutual gravity. But the force from the electric charge is 10 to the power 24 times higher than the attraction they feel from gravity. That's 24 orders of magnitude bigger. So any effect of gravity is lost down in the 24th decimal place of the electrostatic force, an incredibly small effect. So the only test bed of quantum gravity are places where you have a huge amount of matter squeezed into very small volumes, which are always incredibly high energy situations, like black holes or the Big Bang. And unfortunately, these are not things we can create experimentally given our current level of technology. To get to the right energies, we'd need a particle accelerator like CERN, but the size of the solar system with detectors the size of Jupiter to get the right kind of energies. And to create enough energy to test quantum gravity, the experiment would actually end up turning into a black hole. So currently, our best bet for testing our theories of quantum gravity are to look at those natural experiments that have happened for us, black holes and the Big Bang. We do that by using gravitational wave astronomy and measurements of the cosmic microwave background. The cosmic microwave background shows us the very first light in the universe, released about 380,000 years after the Big Bang, covering the entire sky. But this light isn't even in every direction. It contains a fuzziness which you can see here. These little fluctuations are actually an imprint of quantum fluctuations from the Big Bang, when the universe was smaller than an atomic nucleus. Think about how wild that is. It's literally Heisenberg's uncertainty principle painted across the sky. The large-scale structures of the universe, clusters of galaxies and galactic voids, were seeded by quantum physics in the deep past. So this is a clear place where gravity and the quantum world meet. So people are studying the cosmic microwave background in great detail, trying to find patterns in the data to point them in the right direction. But these patterns are incredibly subtle, and we still don't know if our current measurements have the resolution we need to see a signature. We need to apply the same cautious optimism to our gravitational wave experiments. They're really interesting because if there is a theory of quantum gravity, then there should be a gravity particle called a graviton, which is a tiny packet of gravity, a quantization of the gravitational waves. Unfortunately, they're way too small to be seen by our current gravitational wave detectors LIGO and Virgo, which have done an incredible job just to detect gravitational waves themselves. But to see a graviton, they'd need to detect minuscule changes in those waves. This is similar to how it's easy for us to see waves of light, but much harder for us to detect a single photon. And I can't overstate how hard it would be to detect a graviton. In fact, they may never be observable because we'd need to measure a distance smaller than the Planck length, which is impossible according to quantum mechanics. So instead, astrophysicists are looking very closely at the gravitational waves from black hole collisions in the hope that there's some small departure from general relativity. And if there is, then it'll be a tiny clue which we can follow to see what direction to take with quantum gravity. Until we get some new evidence of a departure from our existing very successful theories, we'll never get closer to having a grand theory of everything. Okay, let's take a look at our best contenders for a theory of quantum gravity: string theory and loop quantum gravity. Although I'm not going to spend lots of time on them because they're highly theoretical, very complicated, and I don't really understand them. Quantum field theory says that we've got a field for each of the fundamental particles which all lie over each other in space. And particles themselves are excitations of those fields. And in general relativity, gravity is the curvature of space-time. Now, string theory treats space-time as another quantum field, and so tries to unify gravity with the other forces in one framework. Whereas loop quantum gravity doesn't unify the forces, it attempts to separately work out what the quantum nature of space-time is. So string theory hypothesizes that the fundamental particles and all of their properties are the result of different vibrational modes of one-dimensional strings that live in an 11-dimensional space. And one of these vibrational modes corresponds to the graviton. So it reduces all of the different particles in particle physics down to a single entity, which is a string. The theory's had some theoretical successes, but it's been criticised for not actually describing the real world, which is an issue. Loop quantum gravity starts with general relativity, but attempts to model the quantum nature of space-time at the very short distances of the Planck length. And it implies that there's a minimum possible distance, kind of like a space-time pixel. So these are the most popular proposals for quantum gravity, but there are others. And it's important to state that neither theory has an experimental observation where they make a prediction of something that isn't already covered by quantum field theory or general relativity. Let's zoom out to the big picture again. So what's the point of discovering a correct theory of quantum gravity? What change would it have to the world? Well, being able to understand black holes would solve a huge mystery. Currently, general relativity completely breaks down when space-time becomes infinitely curved. And so a theory of quantum gravity would hopefully solve the many mysteries of black holes. Do they contain other universes? Are they the gateway to wormholes to other universes or to other places in our universe? And what happens to the quantum information of objects that fall into a black hole, which quantum physics tells us is not able to be destroyed? And it might give us an idea about what existed before the Big Bang, and ultimately where the universe came from. Now that's all very interesting, but you might want to know how it would affect us directly. The truth is, I don't know. We'd never know until we have the new theory. But looking into the history of science, every single paradigm shift in the fundamental physics has led to new technologies. For example, understanding quantum mechanics led to the invention of the computer and the whole information age. And to get to a theory of quantum gravity, we know for sure that we'll have to abandon at least one of our fundamental laws of physics. So no doubt when we have a theory of quantum gravity, it will open up possibilities that we can't even imagine right now. And most of all, for me, it would be cool just to understand how the universe actually works. This part of the video is sponsored by Brilliant, a website containing many online courses designed to help you learn science and mathematics. In my videos I can't really get into the nitty-gritty of the subjects I'm talking about, and so Brilliant is a great option if you would like to dig deeper and practice the underlying physics and mathematics. A couple of courses relevant to this video are gravitational physics, where you can practice the fundamentals of Newtonian gravity, and quantum objects, where you can delve into the quantum realm. Actually, answering questions is the best way to learn because it forces you into applying your knowledge, which very quickly reveals what you do and don't know, which is a good thing when you're learning. A whole load of content on there is free to try, and if you like what you see, the first 200 people to sign up for the paid subscription will get a 20% discount off their membership. Just go to brilliant.org/DOS, which lets them know they've come from here. And this link is also in the description below. And thank you to Brilliant for their support. If you like this video and like to help me make more, I've got a Patreon page. Or if you're looking for something to brighten up your walls, I sell many different posters on dftba.com. All of these links are below. Hey, thanks for watching.